Hello, I'm Dan Smith. It's been a while. I've been doing a lot of Zoom talks lately, so it's good to be here in front of an audience. I work on Valhalla, and I want to give a talk about where we're at and what the key features are that we're approaching delivery of right now, and really focus on those key pieces. There's a lot involved in the Valhalla project, and I'll gesture at some of the future things that we want to get into as well, but I want to focus on these pieces that are coming soon. Here's my outline. I'll talk about the project and the problems we're trying to solve. Spend some time on the two main features, value objects, and then flattened heap storage for those value objects. Set aside the JVM design underlying the support for these features for a fourth topic, and then conclude. So the Valhalla project, here's some links. The project page is screenshotted there at the right. We've got some early access builds. We encourage you to go download and play with them. And development on GitHub, you can go get the repository and play with it as well. And some mailing lists that I've listed there. There's a mention on this page that what we could really use from people is to try out the prototypes on your use cases and give us concrete feedback about real-world applications. We've done a lot of exploring of the design space and the theory, and hands-on experiences are a big help at this point. So we started out the Valhalla project with a lot of goals. Some notion of bringing value types to Java. That's become looking for flatter and denser memory layouts, having a growing the language approach to primitives, so kind of turning primitives into something more like classes and turning classes into something more like primitives, unifying those two pieces of the type system into one. Runtime specialization with generics, so we know that primitives can't work with generics, and the reason they can't work with generics is because they're not objects, and generics work on erased objects. Compatible migration, so there's a lot of value type-like entities out there, including in the JDK, and we'd like those to be able to come along for the ride. We have this motto, codes like a class, works like an int, that sort of summarizes what we're after. Here's my condensed goal. We want to bring the benefits of primitives to objects and classes. And there's some other follow-ons. For example, can we bring the benefits of objects and classes to primitives? But this is the piece we want to focus on right now. Let me elaborate a bit. So primitives and objects are different in all sorts of different ways that I've tried to enumerate on this chart. Let me go through it. We've got, I think the initial thing you think about is primitives are just raw data. Objects are pointers to the heap where there's a single storage location where that object's been allocated. And sometimes GC moves them around, but there's always like one canonical place where you can find the object. What you get with that model is objects have identity, primitives do not. Objects are mutable because there's a single location you can find the data. When you do the equals operator on objects, you compare their identities, whereas with primitives, there's no identity, so you're comparing their state. We have locking for objects. Again, you can go find a canonical lock for that object and do things with it. Objects are defined in classes, whereas primitives are built in. That's another kind of separate attribute. There's just the nature of the way the language has been designed. Because they're user-defined, objects have members, fields, and methods, constructors. No members for primitives, just whatever the spec says. These are the operations on primitives. There's subtyping for objects and classes. There's not subtyping for primitives really. To get from one primitive type to another, that's a conversion. And so each primitive type is sort of its own island. Like I mentioned, objects work with generics, primitives do not. With objects, you have nulls. And that's sort of a side effect of having references. And so there's this place where we can say there's nothing here, and we call that null. Whereas with primitives, we don't need a null, and people are happy with just an initial value of 0. Strong encapsulation for objects. It's weaker for primitives in one particular way, which is with races. The spec allows longs and doubles to be corrupted. So yeah, that's a long list, a lot of differences, and we kind of want to rationalize all these and make sure that the things that are on this list are significant and things that we want to hold on to. I want to highlight that direct representation piece. When I said we want to bring the benefits of primitives to objects and classes, really what that means is we want direct representation of freely copyable objects. And if we can do that, that unlocks a lot of optimizations. Let me illustrate. Probably seen some diagrams like this before. So on the left, this is what we get with objects traditionally. I have segments that contain points, an array of points, and every time I refer to a point, that's a pointer to a point. And so the points kind of live in their own space in the heap, and they can be in kind of a jumbled spaghetti of different objects living in different places. On the right, this is what we'd like. The segment object just contains the x and y values for each of the points. The array is just rows of x, y interleaved values. And there are advantages to the one on the left. You can see, like, I've got some sharing between the segment and the array. The array actually contains, at slot 2 and slot 4, the same point object. So there's reasons that it could be advantageous to lay things out, like on the left. But in modern hardware, in a lot of use cases, it's really valuable to be able to have something more like the right, where all your data is neat and tidy and collected in one place. Another thing that we could do if we had more primitive-like objects is stack scalarization. So here I have a couple of methods. Within the draw method, it's got a couple of variables, and your local variables are also pointers off to the heap somewhere. Whereas it would be nice if that start variable on the right-hand side, it's just the x and y. It sort of gets flattened out into the x and y's. This is an optimization that JVMs do for identity objects already, and they do that by trying to analyze, are any of the identity properties going to be needed? And if not, I'll just flatten it out into its field values. But if there is no identity, you know you can do that always, and so that's a nice advantage. Also pointing out that with that mirror method, we're returning a new point, that's an allocation, whereas if we can freely copy these XY pairs around, we can just do a multiple return and copy them directly. We don't need a new allocation. All right, so more concretely, what sort of optimizations could we do if we could have objects that aren't tied to a single location? We can skip out on allocations. We can avoid pointer dereferences. Garbage collection is essentially free with whatever container your values live in. We can have dense storage. In other words, we can leave out all the headers and just talk about field values. And we can have localized storage. So everything lives in the same area of memory rather than having pointers shooting off in different directions. If we want that, of course, there's going to be trade-offs. And so we need to think about what are we willing to give up. And we've already said we're willing to give up the single storage location. We're also willing to give up identity. A lot of times we don't need identity, but we can't have identity and have this primitive-like behavior as well. It also implies no mutation. It also implies the equals operator needs to be operating on state instead of some sort of identity. It means we give up our locks. Also down at the bottom, null it creates some problems for the kind of memory layout we're after. And that strong encapsulation that objects guarantee might need to give up some of that as well. Okay, so all these things we've crossed off are properties of objects that get in the way of the primitive-like behavior that we started out saying we'd like. And actually a lot of them are not particularly useful for applications. Objects come with all this overhead, but sometimes you just don't need all of that. And so the goal in Valhalla is to offer programmers the choice to make those trade-offs. The design principle here is we want the layout optimizations to be an emergent property of semantic things. So there's a lot of different semantic properties in this table. We don't want a keyword that says flatten this object and bake that in. The optimizations that we do today are probably different than the optimizations we'll do in 5-10 years. We don't want another register keyword that is tied to assumptions about hardware and about what sort of optimizations are wanted. We want to express semantics. So that's where we're focusing. Snapshot of where the project is at. We've been at this for a long time, began in 2014. And we've iterated multiple times on expressing value objects in the object model and the type system, expressing value types and type restrictions in the JVM, evolving generics, figuring out how we can make generics work and take advantage of primitive-like behavior as well. It's a huge problem space. It's the behavior of objects is pretty foundational to the Java language and the JVM. And so to go in and lift that up and say we're going to change things is pretty invasive. And so it's a big undertaking. We think we're in a good place with a preview-ready user model at this stage. We've got a solid JVM substrate. We've got optimizations implemented that have been there for a few years now. And actually, a lot of the more recent work has just been to get the user model right to expose those behaviors that the JVM is ready to provide. We also have a preliminary, detailed design for the parametric JVM to handle generics. But that's the next phase. Still needs a lot of work to get there. But we think we've got a good picture now. I want to share some of the details of the user model in this talk. And that starts with value objects. So what is a value object? An object with no identity. Like I mentioned on the chart, it means there's no mutability. All the fields are final. It can store references. You can store final references to mutable state, that's fine, but the object itself needs to have final fields. It's considered the same as any other value object if they're the same class and they have the same field values. So that solves the equals operator problem. And we just don't support synchronization or locking. You try to lock, you'll get an exception. A new term, an identity object, that's just any other object. It's not a value object, and that includes arrays. It's all the objects you're familiar with. So they have those differences on the left. There's a lot of commonality. All objects extend the Java-Lang object class. They all have superclasses and super interfaces. They all have fields and methods. They can have enclosing instances as inner classes, support the same operators, toString equals hash code, that all works. And they're created with new instance creation expressions. So as a programmer, to show you an example, you're not going to notice a huge difference. Oh, okay, one more slide, and then I'll show you an example. But the the general feel is it's just Java programming, and we think that's important. A value class, then, is a class that is marked to have value object instances. That's straightforward. An identity class is a class that says I have identity instances, or that my subclasses all must be identity classes with identity instances. And this works on interfaces too, so I can declare a value interface, I can declare an identity interface. And there's also a third category, neither. So this includes most interfaces by default. An interface can have instances that are both value objects and identity objects. We're not going to try to put all the value objects in their own box in a separate area of the type hierarchy. They can flow freely. And the class object is also a case of a neither. So you can call new object as before and get an identity object that typically gets used for locking. But of course, value classes extend objects. So if you just have a variable of type object, you don't know what kind of thing you're working with. There's some restrictions on value classes that I list there. Has to do with finality and construction and synchronization. Identity classes, there's just the restriction that you can't extend a value class with an identity class. And then because there's a different construction mechanism, that's the one area of incompatibility that we have in value class binaries versus identity class binaries. If you try to switch from one to the other, your constructors will be invoked in the JVM differently. So here's an example. Value class substring. I've just added the key word. Everything else here is pretty much what you would write anyway. The class itself is implicitly final. The fields are implicitly final. Other than that, I write the constructor just like I would an identity constructor. I can implement methods of the super interfaces. A lot of this is, you may be saying, well, why wouldn't you? But there are models in which things like implementing interfaces would not be supported. But we thought it was important to be as class-like as possible. On the left, here's some just normal object things you can do with this value class. Allocate it, have variables with nulls. All of that is just normal. On the right, those are the special behaviors. So first of all, there's the equals operator. What I'm illustrating here is that if I allocate a new substring object, let me show you the fields again, because this operator operates on fields. There's a string and a start and an end index, okay? So any substrings that have the same string, the same start index, the same end index are going to be equal. And if they don't, they're not. So for example, if I allocate another one using the same parameters, that's equal to the S2 that comes from the left. Whereas if I use a different underlying string, even though I want to, this is a lazy operation, so the underlying data is different, but the bit that I'm extracting is the same. That's a different object. One takeaway from this is there's the rule that you really shouldn't use the equals operator for most of your operations. You really want to go with dot equals instead. That still carries over. If you don't want the kinds of field comparisons that you're going to get with equals, you want to call equals. And that, just as a general principle, that's probably the right way to approach your code. And then more illustrations. We have hash code and identity hash code that are defined in terms of all the fields, because there's no identity there. It just works with all the fields. The last bit is just showing the exception you'd get if you tried to synchronize on one of these. So some implications of declaring a value object. In traditional object-oriented programming, everything's an object, there's a unique identity, there's a rich set of capabilities that comes with these, but there's costs, like I talked about. And so As I mentioned, escape analysis can kind of try to identify instances where those costs aren't necessary and then do some optimizations. With value objects, you don't need those sorts of optimizations. You just know that this object doesn't have an identity, and I can copy it around in whatever way is convenient. As a programmer, what should you be thinking when you're writing classes? Just generally use identity if you need it, and if you don't, use a value class. There's no need to include identity in your class if it's not something you're going to use. You don't want incidental identity like we have with javelin integer, where you can create two different integers that represent the same thing, but depending on where they came from and what range they fall in, they may be different objects. In general, programming in this environment, you don't want to assume that some random object somebody gave you is your own, that you own it. That's a bad practice anyway if you don't know where it came from. But now you've got value objects where I may have this value object, but somebody else, anybody who can create new ones, can create another, and it will be equal to the one that I have. And we support migration. So I mentioned things like local date, even javelin integer. We want to turn into a value class. And that's in general possible as long as you don't trip over if you don't have a public constructor that people are relying on, then you can make that migration. Here's some profiling results that are interesting. So this is results from our actual implementation right now. On the top, that is using an identity object. This is an operation that does some image processing. It's somewhat realistic. It's just my hacked together example of blurring an image using some neighboring pixels. And so all the objects that I'm created there's gigabytes of objects that I'm creating by programming in a way that most image people would probably not like to see, which is every single pixel and every computation on a pixel allocates a new object. So lots and lots of objects being allocated. The purple line, that's the GC kicking in and pushing down my usage. So this tends to be fairly local in this case. I'm just operating on stack. And the GC is actually really good at these sorts of problems if you throw it at it. Depending on what you do and what else is going on in your VM at the time, that may or may not be a problem to be allocating all these objects. The good news about value objects is when I do all those allocations, it's just free. There's no GC happening. There's no allocations happening after warm-up. So that's nice and clean. One important side effect besides the performance impact is if I'm confident my objects are not going to be creating all this memory pressure, then I'll feel a lot freer to use them and to express my program in the natural way that I'd like to. So rather than having somebody passing in a buffer that I can fill in, I'll just allocate an object and give it to them. And it's a value object, and everything gets optimized away. I should emphasize that this is not only local to a single method, but this optimization works across calling. It's a calling convention optimization. So you can have a call stack that passes value objects up and down, and all the allocations can be skipped. All right, that's the top half of our chart that we looked at before. We've given up identity, mutability, identity comparisons, and locking. We've gained direct representation and the performance benefits that come with that, with an asterisk. So this is all stack optimized at this point. We haven't looked at Heap, and Heap has some additional problems. There's also an asterisk on subtyping. So a value class has supertypes. If I take a value object and assign it to one of those supertypes, at least as implemented right now, you're giving up the benefits of flattening in order to get polymorphism. And so the point of that assignment internally, a heap allocated object gets created to be used with the polymorphic code that wants to operate on it. And the implication then for generics is if I pass something into a generic data structure, that the generic is operating on Java-Lang object, so whatever I pass in is going to get allocated. So try doing some things with array list, and you'll quickly see that you've just got a bunch of heap allocated objects. So that continues to be a problem. Part 2, flattened heap storage. Okay. Let's talk about null. So why do we have null? Well, we need to initialize variables to something. And if I create an array of objects, we don't have a good way to guarantee that array gets initialized. So the design of Java 1.0 was fill it in with null. That thing can't be a class instance. I can't just create arbitrary objects to fill in there. We'd have to run a constructor, and we don't want to do that. We want it to be fail fast. So one strategy you could imagine, I guess, is the C strategy, is just have garbage data and you read it and you get whatever's sitting there. We don't want that. So for safety, null acts as a barrier. It's a cheap barrier, but you fill in zeros and then you've got that data, and when you try to operate on the object, it's fail fast, lets you know that you don't have a real object there. Why is this a problem for flattening of value objects? Well, it requires an extra 1-bit flag, or some way to say not only to cover the entire domain of my value class, but also I need a bit that says this thing is null. And for alignment reasons, once you've added 1 bit, in a lot of cases, you've doubled the size of your object. So that's not going to work for many use cases. We don't want our int-like array to use 64 bits for each int. So beyond that, it's also difficult to manage a null flag with races. You can get into scenarios where if I have a null flag and one thread sets that flag to true or to null, and another thread's writing data into the same storage location, you end up with some bits that represent null and also represent a pointer off to some object, and that creates all sorts of GC problems. You have nulls that you can get memory leaks with nulls. So difficult to handle null in flattened heap. And we've thought some about it and decided let's set that aside and let's focus on the straightforward case of if there's no null. So if we don't have null, what are we going to initialize our data to? We'll call that an initial instance of a value class. That's what you get at the start of your constructor. If you just return right out of your constructor, you've got an initial instance. So all the fields are zeros or nulls or false, whatever their default values are. That instance, it's a class instance, it's a real object. So invoke methods on it, you're not going to get an MPE. And for some classes, that's great. So point, for example, the point 0, 0, that's a really good object that I'm happy to operate on, and I'm happy with my array being filled with 0, zeros. Local date, that's a little trickier. So year 0, month 0, day 0 is not actually a valid encoding of a date. We could change the encoding of the fields, of course, but what are you going to set it to? Do you really want 1970 January 1st to pop up in all of your code operating on dates? That's local date's sort of a different category. Optional is in the first category, where the optional that represents empty, that's a really good default value. An address where the street and the city and the zip code are all nulls, that's not good. So this needs to be an optional property, is the point. And the way you get that property is with implicit constructors. So a class can declare its constructor implicit, or a constructor that's implicit, has 0 arguments, it has to be public. And what that conveys is not only can you invoke this constructor and it will just return the initial instance, but also the JVM is free to just create those initial instances without running any code at all. There's also a foo.default that says just give me that initial instance without trying to run any code. So here's a color class that has an implicit constructor, and what that means is when I call new color, I get the same thing as if I set everything to 0. And when I call new color, I get the same thing as color.default. The other element we need in order to eliminate the nulls is some way to say this variable isn't expected to have a null. So we have a new kind of type, a null-restricted type that can be applied to variables. On the right, you see me allocating a color array, and the exclamation mark means no nulls here. What you get when you allocate or declare a null-restricted type on a value class typed variable is it rejects assignments from null. So you try to write a null in there and it will blow up, it'll throw an exception. You see that at the bottom of my code example. It also initializes the storage to the class's initial instance. So when I'm calling these red, green, blue methods from a fresh array, those methods work and they return the zeros that are in the underlying object. There's a lot more that could be said about nullness features. Right now, our goal is just to support null restriction on value classes that are implicitly constructible. So it's a narrow set of classes that can use this feature. But there's a path towards, let's apply this to everything. And we like the idea of this is a general purpose feature, not just a specific, in the past we had .val and .ref as specific value and reference types used by value classes. We like this a lot more as a general purpose feature that conveys the information we need, in this case, conveys the semantics we need. And I've listed a future work for nullness there on that slide. We can talk about that more later. Third element that we need to consider is concurrent reads and writes. Talked about that a little before. In general, the rule for programming is don't have races. You have races, bad things will happen. And that was a pragmatic approach to getting performant code in the early days of Java, and it continues to be. So the overhead of ensuring atomicity for flattened data, depending on how big it is, can get quite large. And rather than forcing that overhead on everyone, we want to offer people the choice. So what happens if you have a race, you've got buggy code, and it accesses a null-restricted field or array? If the value class is small, then it'll just be atomic, and that's fine. The usual anomalies about the memory model, what happens before what, that you might still observe those. If it's a large value class, then by default, we're going to ensure atomicity. But if you opt out by implementing a certain interface, loosely consistent value is the name we're playing with right now, then that interface says that this class may have new values that pop up. The implicit constructor not only allows for a default value, but also other strange values that might arise out of races. We'll tolerate those too. That's a programming choice again. So by default, strong encapsulation. If you're willing to give things up, then you get better performance. First of all, giving up the all zeros, control of your instances, willing to tolerate an all zeros instance floating around. And then further, maybe I'm willing to tolerate these sorts of mixed and matched, racy objects. As an author, what am I going to think about? At the declaration site, what are these values meaningful in my domain? So some classes, it's fine. Other classes, you think of like a range object, so it has a start and an end, and the end and start need to be related, and that's validated in the constructor. You don't want random mixes of starts and ends. That would have all sorts of unpredictable results. So some classes are willing to give up control over construction a little bit more, and as you take those steps, you enable better optimization. At the use site, there's also a choice to make. Do I need null here in this storage? If I do, fine. We can handle that. If I don't, give it up, and you get some optimization. So to sort of illustrate what I need to do to get effective flattening, and this is as of what we've implemented right now. Future optimizations may be more ambitious. We may be able to handle nulls in an effective way. But for now, first of all, for a small class or a large class or many fields you have, you need to give up identity. Second, you need to give up implicit or offer implicit construction. And third, you need a null restricted variable at your use site. Do all those things, and you can expect flattening. It's a JVM choice, and it's an optimization, and there are corner cases. If you have 100 fields, it probably won't flatten. But those are the key bits of semantics that you need to convey to provide the JVM the opportunity to flatten. If your class is larger and we're going to need the overhead of atomic guarantees, then implement loosely consistent value to opt out of those if that works for your class. I want to illustrate this. If I can get to my terminal. So I downloaded some NBA data, all the stats since 2003, I think, of every game, every player's box scores, and used it to generate an array of what I call the events in a game. So each shot taken represents an event, each rebound, etc. And let me illustrate. It's got about 1 million elements in this array. Each one is an object that has some pointers to different things. I'm querying that data now. So here's my array of events. It has around 1 million elements. I'm querying that for a 3-point shot history of every team. And so I'm running the same query multiple times for each team. It takes about 123 milliseconds here. If I switch from an identity class representing my array storage to a null-free value, then we get a pretty good speed up, around 90 milliseconds. So it's like a 20-30% gain. Another thing I noticed is I populate this array sequentially, just reading in data, plugging things in. If the data came from somewhere that wasn't so uniform, well, let's try shuffling all those objects and see what we get. Now we're like around 600, 700 milliseconds. So about a 6x, 5x or 6x or something slow down in order to run the queries across this array with pointers going off every which way. And the reason for that is because there's a lot of cache misses, right? So it has to go to cache, bring in the data, next element, go find the data somewhere else. Whereas if I go back to null-free, as you would expect. It's just the data. So it's all local. There's nothing new here. Execution times can be pretty similar. So the advantages can vary widely depending on what sort of memory layout you have and a lot of idiosyncrasies. And like I mentioned before, I think the big advantage of using value classes and using null-free storage, et cetera, giving up the things that you don't need, is then you can be confident you'll probably get the best performance you can get. There is a trade-off here that I guess is worth highlighting. If all you want to do with your data is shuffle it, then the value classes are a little bigger, right? So this is 3,200 milliseconds. Shuffling my pointers was faster. So it's not always a win. It depends what you're doing. If all you're doing is moving pointers around, pointers are actually probably more useful. But once you track that pointer to its memory location, then you hit all the overhead of memory accesses. So I think, anything else I want to say about flattened heap storage? So in general, use no restricted storage of value class types, and it can be pretty reliably flattened. Then you get writing into the data without allocations, read without any indirections, and sequential storage, so no cache swapping. So back to the goal of giving objects some of the advantages of primitives. Now we've given objects the ability to have non-null storage and to have default values. We've also relaxed the encapsulation requirement so that there's potential for corruption under race by giving up some overhead of atomic guarantees. All right, that's looking pretty good now. What about those other rows? Well, those are things we like, actually. It's good that value objects can be defined by classes, that they have members, they have subtyping, they work with generics. Those are all great. So if you want to work with polymorphic code, with supertypes, with interfaces, you're going to need heap allocation to do that. And if you want to work with generics, you're going to use heap allocation for that. We have a good picture for what to do about generics. Maybe there's optimizations if it's useful for things like sealed interfaces as well. We've thought some about. All right, final. I'm going to try to go about 10 to 15 more minutes here. JVM. Let me illustrate some of the underlying JVM capabilities. So what do we need for value classes? First of all, I talked about identity classes and value classes. That's a JVM property. So we have a couple of new class modifiers. An interesting thing here is that identity classes are by default your concrete classes and abstracts without without certain properties. Interfaces should not be identity by default. And so we actually have this ACC super bit sitting there in the class header that doesn't do anything anymore, but it still gets set. And it actually turns out if you just use ACC super and say, we're calling that ACC identity now, it doesn't exactly get everything you want, but it's a good starting point. It's a good way to interpret legacy classes. So sort of as a help to tooling, we think it's a good idea to reuse that bit and just rename it to ACC identity. There's some extra rules for ACC value classes. Ensure that you're using final appropriately, you're not using synchronized. And at the point of loading the class, we'll check the super hierarchies, make sure you don't have identity value clashes. So that's the flags. Instance creation, I mentioned this is different. So because there's no identity and no mutation, that's the underlying mechanism of construction. Call a superclass, let it mutate some state, and then return. So we can't do that. We need a new construction mechanism. And we're calling that a vnew method with angle brackets. The vnew method is basically just a static factory. And The Java language is going to use it for its constructors, but it's a factory. You can do with it what you want, really. It's just a special name that gets highlighted as the thing that came from a constructor. There's a couple of new opcodes that will get used in those methods. The first is aconst init. That gives you the initial instance of the class. The second is withfield. Withfield takes an instance, creates a duplicate, and sets the field to a certain value. So again, no direct mutation of state. This is cloning with a different with a different field value. And then the third element we need is everything in the class file, the use site, looks just the same, whether you're operating on an identity class or value class. So how are we going to let the VM know that this particular field has a special type that you might want to optimize the layout of, or this particular method has a different type in its signature? And what we've come up with is this attribute named preload that indicates to the VM, here are some classes that you're going to want to go look at. It doesn't validate anything. It just points out some classes. Go look at the classes. If the VM loads them and sees that they are value classes, it may want to do some optimizations with that information. Okay, and then for flattened heap storage, what do we need? First of all, an attribute that indicates the implicitly constructible property of a class. Thought about doing that with the init method, but it doesn't seem like a good fit. Or I guess it would be the vnew method. Put something special on the vnew method. We kind of think we'd like a separate attribute that expresses this property. And then just by convention, your vnew method returns aconst init. So you'll get the same thing whether you explicitly call it or the JVM creates the object for you. We also have the super interface I mentioned for non-atomic reads and writes. At the use site, it's an interesting problem of how do we capture the idea of null-free storage. And one thing that we're thinking about is we're entering a phase in the life of the JVM where we're going to add these, and when we get to generics, we're going to add some new type-like things as well. There's going to be a family of new kinds of types, but we don't want descriptors to blow up. And I mentioned we're interested in compatibility. We don't want changing the nullness of a field to break binary compatibility. So there's a distinction that is useful between the linkage type of a field or a method and the restricted type. We're calling them type restrictions on that storage. And the type restrictions are just a side information that is enforced dynamically that says, in this case, don't put nulls here. And also initialize to the initial instance. So the type restriction sits to the side. It's not a type. It's not something you're going to get a Java-Lang class from. It's some other thing. But it just expresses the constraint. And then the JVM can use that to implement certain semantics and then optimize with those semantics. Have some examples of what it might look like to compile from these bang types in the language to the underlying class file. So there's kind of a mixture. It's in some sense erased. We just continue to use L types. And then in certain places, we insert null restrictions. All right, to conclude, where are we right now? I think we're really happy with where the design has landed. We've found a good place where the new concepts, I think, are fairly light. They kind of fade into the background if you don't care about them. Heavy on migration compatibility, so you can actually take local date and get flattened local dates in an array And all the old code that operates on local dates still works, so that's really nice. Value objects are designed and implemented. The flattened heap storage piece needs a little more design, as you saw there on the slide, at the JVM level. So we're working through those details. Like I mentioned, the major optimization work has been done for quite some time. There's some implementation work in the VM needed to align with wherever the class file format ends up and make sure the interface into those optimizations is supported. We expect to have an early access release with these features this iteration coming soon, and we're working towards a standard preview feature with those two things. There's some future work on the other side. I mentioned nullness, I mentioned generics, I mentioned making primitives more like objects. These are all things that we're setting aside for this phase, and we'll come back to them in the next phase. Other uses for type restrictions. Maybe there's more optimizations that we'd like to do. And of course, once these tools are in the VM, that unlocks a lot of great library work that can happen. So looking forward to those pieces. And that's all I've got. So thanks. Appreciate listening.